This video is going to be on the Maxwell-Boltzmann distribution and evaporative cooling. So this picture I drew over here is a picture of the Maxwell-Boltzmann distribution, or roughly. It's a rough sketch. And what we have is on the y-axis number of molecules and on the x-axis kinetic energy. This is generally used for gas. So I also reminded you how we can think of a gas. Kind of just think of them as like ping pong balls or tennis balls or something, all moving really fast and bumping into each other. And remember that temperature is a measure of the average kinetic energy. So for each one of these lines up here, I drew an arrow, which represented the average kinetic energy. And you can see I drew three different curves, one for 100 Kelvin, 200 Kelvin, and 300 Kelvin. And as the temperature increases, the average kinetic energy increases, right? And that should make sense because that's kind of what temperature is. And you can see that the shape of the distributions is a little bit funny, and it kind of changes as the temperature goes up. And the really important thing to notice is that as the temperature goes up, the energy that the molecules have goes up. But not all molecules have the same amount of energy. And you can think, similar to in our dice game, if we had all these kind of gas particles moving around and hitting each other, some of them, for whatever reason, for like kind of statistically, it just so happens, would end up going really, really fast at a certain moment, right? Say three particles hit it all from behind and go zooming off, but then in the next instant it transfers a lot of the energy to another molecule. So now it's going a lot slower, right? And so these kind of jump around as time goes on, but in general we can predict what the distribution will look like, and it will look something like these. And one of the really important parts is that they all have this tail. So on the really at the very end, it seems a little longer than it should be. And I guess it's easiest to tell maybe in my first picture, the 100 Kelvin one. And you can see that there's this little extra tail where there's some molecules that have a lot of energy compared to the average. And in thinking about an analogy or something, you could think about a kind of wealth distribution. So these different temperatures would represent maybe different countries, and so that there was like an average income for each country. But there's always this small number of people who have way more money than the average, right? And regardless of what kind of country you're in, there's always going to be someone who has more money than the average. And those are the molecules that I want to focus on right now for evaporative cooling. And so if we go to my picture down here, we have a puddle, right? So it's a puddle of water, and I drew another kind of distribution just to get the rough idea. And it's at 20 degrees Celsius. And even at 20 degrees Celsius, right, the particles aren't moving that fast for liquid water, but there's going to be some that are moving way faster than the normal ones. And they're actually moving so fast that if they're at the surface of the puddle and they happen to be going up, they'll have enough energy to break free from the other molecules, right? So that there'll be enough energy transferred to them that they can overcome the attraction from the other molecules, right? So this would be adding their potential energy. So they actually have the ability to become a gas. Right? And I kind of shaded in this tail here to show that these molecules here could become a gas. Like, right, these are the ones that have so much energy that, man, they could become a gas. And then over here, I have 100 degrees Celsius. So this is water at its boiling point. And there's some things going on at the boiling point that we're not really going to talk about. But the really important thing to see is that if I draw that line at the same spot, right, just about this far apart from the 0 point, I try to make it about equal. There are way more molecules, right? The majority of the molecules have that amount of energy. And that kind of means that, again, in this kind of loose terms, they could become gas if they aren't already gas, right? They have so much energy, they might actually already be gas right now. But because it's at a much higher temperature, this happens very rapidly. That's why you could boil a pot of water really quickly and get it to completely become gas. Whereas in a puddle, it takes a few days, right? And the warmer it is outside, the faster the puddle will disappear. So another interesting point here is evaporative cooling. And so evaporative cooling is just saying that, okay, if only the fastest molecules can leave, only the molecules with the most energy can leave, in like a puddle that's evaporating, that once they leave, they take way more energy than is kind of like the average with them. So it actually decreases the average. That would be like saying the richest people in a country go to a different country and live there. What happens to the average income? It has to go down because there's really rich people left. And that, translating that into kinetic energy terms, it means that the puddle actually cools down. And this is why we sweat. We kind of cover our skin in some water. The most energetic particles evaporate, and it ends up cooling down the rest. And that's why we cool off. And that's evaporative cooling.